Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a question that feels simple at first, but slowly opens into something much deeper. Why the universe is almost completely empty, and why that emptiness may not be an accident at all. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a gentle reminder of how many small corners of the world are awake together in moments like this. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the emptiness of the universe together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. If you've ever stepped outside on a clear night, far away from the glow of city lights, you've probably had a moment where the sky felt full. Not just filled with stars, but almost overflowing with them. Tiny points of light scattered across the darkness, some faint, some bright. A soft band of mist stretching across the sky, the Milky Way, like a river made of distant suns. It gives the impression that space is crowded, alive, and densely packed with shining objects. It feels like abundance. Like if you could just travel far enough, you would move through a universe rich with stars in every direction, always surrounded, never alone. And in a way, that feeling makes sense. Your eyes are telling you something real, but they are also telling you something incomplete. Because every single star you can see with your naked eye, every tiny sparkle in that vast sky, is part of a very small neighbourhood. They all belong to our own galaxy, and even within that galaxy, you're only seeing a thin slice of it. The Milky Way stretches across about 100,000 light years from one side to the other. A light year, just to pause for a moment, is the distance light travels in 1 year, moving at about 300,000 kilometers per second. It's an almost unimaginable distance, and yet the galaxy spans 100,000 of those. But the farthest stars your eyes can pick out in the night sky are only about 15,000 light years away. That means, without realizing it, you're seeing only a small fraction of your own galaxy. A local bubble of light surrounding your position within it. It's a bit like standing in your backyard looking round and quietly assuming that the entire Earth must look just like this one patch of ground. Comforting, familiar, but not quite the full picture. And then there is something even more surprising. Your galaxy, the Milky Way, is not alone. There are hundreds of billions of galaxies in the observable universe, each one filled with its own stars, its own structure, its own history. So at first, this seems to confirm the feeling we started with. If there are that many galaxies, each with billions of stars, then surely the universe must be full, overflowing even. But this is where a gentle shift begins to happen, because what we feel, and what is physically true, are not always the same thing. To understand what the universe is really like, we have to do something slightly different. We have to stop simply looking and begin measuring. Imagine pointing a powerful telescope, not at a bright star, not at a glowing nebula, but at a patch of sky that looks completely empty. Just darkness, no visible stars, no light, nothing that stands out at all. In the mid-1990s, astronomers did exactly this. They chose a tiny region of the sky, so small it would take millions of those patches to cover the entire sky, and they stared at it for days, letting the telescope collect every faint particle of light that arrived from that direction. At first, there was almost nothing, But slowly, as the light accumulated, something began to appear. Not emptiness, but thousands of distant galaxies, each one a vast system of stars, some larger than our own Milky Way, some smaller, all incredibly far away. What looked like darkness was, in reality, filled with structure far beyond what the human eye could ever detect. And this led to a quiet, almost paradoxical realization. Everywhere we look, even into the darkest parts of the sky, there are galaxies. Every direction contains more than we can easily comprehend, so the universe must be full, right? It's a natural conclusion, and yet something doesn't quite add up. Because seeing many things is not the same as those things taking up much space, and this is where the story begins to change, very gently, almost invisibly at first. The universe may be filled with objects, but those objects are separated by distances so vast that, in between them, there is almost nothing at all. It's like standing on a quiet shoreline at night, looking out over the ocean. You might see a few distant ships, each glowing softly against the horizon. From your perspective, the sea feels populated, alive with lights. But if you were to travel out there, into the dark water between them, you would find something very different. Long stretches of emptiness, cold, silent, uninterrupted space between each island of light. And the deeper you go, the more that emptiness becomes the dominant experience. This is what the universe is like. Not a crowded city of star, but a vast, almost endless ocean with only a few scattered islands. And even those islands are mostly empty themselves. But we'll come back to that. For now, just hold on to this feeling. The sky looks full. It feels full. But that fullness is a kind of illusion, a local richness, surrounded by something far quieter, far larger, and far more empty than our eyes can easily understand. And as we move forward, we'll begin to measure just how empty it truly is. Not in vague impressions, but in numbers so extreme they almost lose their meaning. Because the universe doesn't just contain emptiness. In a very real sense, it is emptiness, and everything else is the exception. If you stay with that feeling for a moment, that quiet sense that what looks full might actually be something else, you begin to notice a subtle shift in how you see the night sky. Because once you question what your eyes are telling you, curiosity gently takes over. What happens if we look deeper? Not just with our eyes, but with instruments designed to see what we cannot. Imagine again that same patch of sky, a place where, to your eyes, there is absolutely nothing. No stars, no glow. Just a dark, empty space between the brighter points of light. It's the kind of place your gaze would normally drift past without a second thought. But now, instead of glancing away, we linger. We point a telescope at that darkness, and we wait. Not for a moment, but for hours, and then days, letting faint traces of light slowly gather, like droplets forming in silence. This is exactly what astronomers did when they created what is now known as the Hubble Deep Field. They selected a region of sky so small that if you held a grain of sand at arm's length, it would cover a similar patch. Just a tiny window into what seemed like nothing at all. And then they stared into it for 10 days. What emerged was not emptiness, but thousands of galaxies, each one a vast collection of stars, each one containing millions or billions or even hundreds of billions of suns. Entire systems of light, layered one behind another, stretching deep into space and back through time. What had appeared to be empty was anything but, and when this experiment was repeated in other parts of the sky, the result was always the same. Wherever we look, even into darkness, we find more galaxies, more structure, more light, more complexity. At first, this feels like it settles the question. The universe is not empty, it is full, rich beyond imagination. And yet, something about this conclusion is quietly misleading, because what we are seeing is not density, but distribution. There is a difference between many things existing and those things being close together. To understand that difference, it helps to slow down and gently shift perspective again. Let's imagine for a moment that you could step outside the Milky Way. Not physically, of course, but just in thought. You drift away from our galaxy, watching it shrink behind you, its spiral arms slowly folding into a faint blur of light. You continue outward, passing the space between galaxies. At first you might expect that journey to be filled with sights, but instead something else happens. There is nothing. No stars nearby, no glowing clouds, no visible structures, just darkness stretching in every direction. The nearest galaxy might be millions of light years away. That means that even travelling at the speed of light, a speed so fast it circles the Earth more than 7 times in a single second, it would take millions of years just to reach the next island of stars. And in all that time, you would pass through almost entirely empty space. This is the part that's easy to miss when we look at images filled with galaxies. Those images are carefully framed. They show you where the light is. They do not show you the vast silent regions in between. It's a bit like looking at a map of cities at night. You see glowing clusters, New York, Tokyo, Paris, bright points scattered across the darkness. And from that map, it's tempting to feel like the world is covered in light. But between those cities are oceans, forests, deserts, mountains, large stretches where there are no lights at all. The lights are real, but they are not the majority. And the same is true of the universe. Even though there are trillions of galaxies, the distances between them are so immense that most of space remains empty. And as we begin to measure those distances more carefully, the scale of that emptiness becomes almost difficult to hold in your mind. Within our own galaxy, stars are not packed closely together. The nearest star to our Sun is about 4 light years away. If we imagine shrinking the Sun down to the size of a tiny grain of sand, then the nearest star would be another grain of sand, placed tens of kilometers away, not meters, not across a room, but across an entire city. And everything in between would be empty. Now expand that idea outward. Galaxies themselves are separated by distances that are even more extreme. Our nearest large neighbouring galaxy, Andromeda, is about 2.5 million light years away. Between us and it, there are only a few small galaxies, scattered sparsely. The rest is vast, quiet space. And this is considered a relatively crowded region of the universe. In other areas, galaxies are even farther apart. There exist enormous regions called voids, places where you could travel for hundreds of millions of light years and encounter almost nothing at all. Not completely nothing, but close enough that the difference becomes almost philosophical. And yet, despite all of this, the illusion remains. Because when we look through telescopes, we often see images filled with galaxies, clustered, layered, abundant. But those images are like snapshots of rare gatherings. They capture the places where matter has collected. They do not show the overwhelming emptiness that surrounds them. And this brings us to a quiet but important realization. The universe does not hide its contents from us. It reveals them, but it does so in a way that emphasizes what is there, not what is missing. And what is missing is almost everything. So we arrive at a kind of paradox. Everywhere we look, we find galaxies, and yet, almost everywhere we go, there is nothing. Both statements are true, and holding both of them at once is the beginning of understanding what the universe is really like. It is not a place where matter is spread evenly, like dust floating in air. It is a place where matter gathers into rare, delicate structures, surrounded by vast, silent expanses, like islands in an ocean, like lanterns in a long unlit road, or like thoughts, drifting in the quiet space of a resting mind. And as we continue, we'll begin to move from this sense of distance into something even more surprising. Because it turns out that even the things we call solid, even the stars themselves, are not nearly as full as they seem. As you sit with this image of the universe, filled with islands of light yet surrounded by vast stretches of darkness, there is a natural question that begins to form. Just how empty is it really? Not in a poetic sense, but in a measurable one. Because until now, we've been speaking in impressions, in feelings, in comparisons. But science, in its quiet way, asks something more precise. It asks, if we could take everything that exists, the stars, the galaxies, all the visible matter, and compare it to the total space available, what fraction would it actually fill? And the answer, when we approach it gently, is almost difficult to believe. Let's begin with something familiar. A single star, like our sun. The sun is enormous by human standards. Its diameter, the distance from one side to the other, is about 1.4 million kilometers. You could line up more than 100 Earths across its width. It feels large, solid, substantial. But in the context of space, even something that vast becomes surprisingly small. To understand why, we can imagine the sun not just as a size, but as a volume. Volume is simply the amount of space something occupies. For a sphere, like a star, that space grows very quickly as the size increases. If you double the radius, the volume doesn't just double, it increases many times over because space expands in 3 dimensions. Now, instead of focusing on one star, imagine all the stars in the observable universe. There are, by current estimates, on the order of a few 100 billion galaxies, and each galaxy on average contains tens of billions to hundreds of billions of stars. If we gently combine those numbers, not worrying about exact precision, but simply aiming for a sense of scale, we arrive at a number so large it almost loses meaning. Something like a few hundred sextillion stars. That's a number with more than 20 digits. It feels at first like it must fill everything. But now we place that number into context. We ask, how much space does the entire observable universe contain? The observable universe is not just large, it is unimaginably vast. Its radius, the distance from us to the farthest regions we can observe, is about 46 billion light-years. And a light-year, as we've softly mentioned before, is the distance light travels in a full year, moving faster than anything else in the universe. When we take that immense radius and imagine the volume it encloses, we're dealing with a space so large that even our largest everyday comparisons begin to fall apart. Now comes the quiet comparison. We take the total volume of all stars combined, and we place it beside the total volume of the observable universe, and what we find is something almost startling. The fraction of space occupied by stars is so small that when written out, it begins with a decimal point, followed by dozens of zeros, before a single non-zero digit appears. It is not just small, it is almost nothing. To give this a softer shape, let's imagine shrinking the entire observable universe down to the size of the Earth. All of it, every galaxy, every void, every region of space. Now compress that entire cosmic volume until it fits into a sphere the size of our planet. If you then gathered all the stars in the universe and placed them into that scaled-down Earth, they would not fill oceans, they would not fill continents, they would not even fill a single mountain. They would occupy a space smaller than a single grain of dust. In fact, even smaller than that. Closer, perhaps, to something like a tiny particle, so small that you could barely see it. And everything else, all the rest, would be empty. But there is an even quieter layer beneath this, because up to this point we've been treating stars as if they are solid objects, dense, filled, complete. But that too is an illusion. If we gently step inside a star, not physically but conceptually, we find that matter itself is not what it seems. Atoms, which make up everything we know, are mostly empty space. At the centre of each atom is a nucleus, incredibly small and dense. Around it, electrons exist not as solid particles orbiting like tiny planets, but as a kind of soft, shifting presence, a probability, a cloud of possibility. And between that nucleus and the outer boundary of the atom, there is almost nothing. If an atom were expanded to the size of a large stadium, the nucleus would be like a tiny speck at the centre, and the rest would be open space. So even within matter, within the stars themselves, emptiness dominates. This means that when we say stars occupy almost no space in the universe, we're already being generous, because most of what we are counting as occupied is in reality empty within itself. It is emptiness nested inside structure, space within space. And this realization begins to shift something deeper. The universe is not simply a place where empty regions exist between objects. It is a place where emptiness is the default state, where structure is rare, where matter gathers into delicate temporary forms, floating in a vast background that contains almost nothing at all, and perhaps even more quietly. It suggests that what we call something is often just a thin pattern laid across an ocean of nothing, a pattern that feels solid from within, but dissolves when viewed from afar. As we move forward, this idea will continue to unfold, because the emptiness of the universe is not just a matter of distance or scale. It is connected to deeper forces, forces that shaped how structure formed in the first place, forces that allowed galaxies to exist at all, and that now slowly pulling them apart, and somewhere within that balance and between formation and separation, between gathering and drifting, we begin to see that emptiness is not just present, it is inevitable. If you let that idea settle for a moment, that even the most solid things are mostly empty, it begins to feel as though the universe is built on something quieter than we expected. Not just space, but structure hidden within space, because there is a question that naturally follows. If the universe is so empty, if matter is so rare and so spread out, then how did anything come together at all? How did stars form? How did galaxies gather? Why didn't everything simply drift apart, forever thin and evenly scattered? To answer that, we have to look at something that, in a very real sense, we cannot see. Something that does not glow, does not reflect light, and doesn't interact with us in any familiar way. And yet, it is everywhere. Astronomers call it dark matter. But that name is less an explanation, and more a placeholder for a mystery. To understand how this idea emerged, it helps to go back to a quiet moment in the early 20th century. An astronomer named Fritz Zwicky was studying clusters of galaxies, large gatherings, where hundreds or even thousands of galaxies are bound together by gravity. He was measuring how fast those galaxies were moving. Because in a system held together by gravity, motion tells a story. If the galaxies are moving slowly, it means the gravitational pull holding them together is relatively gentle. If they're moving quickly, then something stronger must be keeping them from flying apart. So Zwicky did something simple in principle. He observed the speed of the galaxies and then estimated how much mass would be required to keep them bound together. Then he compared that number to what he could actually see. to the stars, the glowing gas, the visible matter, and what he found was unsettling. There wasn't enough, not even close. Based on what was visible, the galaxies in those clusters should not have been able to stay together. They should have drifted apart, slowly dissolving into the surrounding space, but they hadn't. They were still there, moving quickly, yet somehow held in place. Zwicky suggested that there must be additional mass, something invisible, providing the extra gravitational pull. Mass that did not emit light, mass that could not be directly observed. At the time, the idea seemed strange, almost unnecessary, so it was largely set aside. But decades later, another astronomer, Vera Rubin, began studying something closer to home: individual galaxies. She looked at how stars move within them. In our own solar system, there is a familiar pattern. Planets closer to the sun move faster. Planets farther away move more slowly. This happens because gravity weakens with distance. The farther you are from the central mass, the less tightly you're pulled, and the slower your motion becomes. So when Rubin measured the speeds of stars at different distances from the centres of galaxies, she expected to see a similar pattern: faster near the centre, slower toward the edges. But what she found was something entirely different. Stars far from the centre, in the outer regions of galaxies, were moving just as fast as those closer in, sometimes even faster. It was as if the outer parts of the galaxy were being held more tightly than expected, as if there was additional mass, extending far beyond what we could see. And once again, the visible matter wasn't enough to explain it. Something else had to be there, something unseen, but gravitationally real. As more observations were made, across many galaxies, across many clusters, this same pattern appeared again and again. There was always more gravity than visible matter could account for, and slowly, the idea that had once seemed unlikely began to take shape as something unavoidable. The universe contains a form of matter that we cannot see, matter that does not interact with light, matter that reveals itself only through gravity. Today, we estimate that this dark matter makes up a little more than a quarter of the total energy and matter content of the universe. While everything we can see, stars, planets, gas, dust, and even ourselves, accounts for only a small fraction, about 5%. So when we look at a galaxy, its bright stars, its glowing clouds, we're only seeing the surface. Beneath that visible structure lies a much larger invisible framework, a kind of gravitational skeleton. Imagine for a moment a city at night. You see the lights, buildings, streets, windows glowing softly, but the lights are only a small part of what holds the city together. There are roads beneath the surface, foundations, infrastructure you cannot see, but which gives shape and stability to everything above. Dark matter is something like that. It forms vast halos around galaxies, enormous spherical regions extending far beyond the visible stars. The Milky Way, for example, has a bright disk about 100,000 light-years across, but its dark matter halo stretches several times farther than that, and it contains far more mass than all the stars combined. It is this invisible halo that holds the galaxy together, that keeps stars moving in stable orbits, that shapes how galaxies interact, merge and evolve over time. Without it, galaxies as we know them might never have formed. In the early universe, matter was spread out, almost evenly. Tiny differences in density, small variations in how much matter existed in one place versus another, were the seeds of all future structure. But ordinary matter, the kind that interacts with light, faced a challenge. As it began to collapse under gravity, it heated up, and as it heated up, it emitted radiation. That radiation pushed outward, resisting further collapse. It was a delicate balance. Too much pressure and matter would spread back out. Too little and it would collapse too quickly. Dark matter, however, behaved differently. It didn't interact with radiation. It did not feel that outward pressure, so it could collapse more freely, gathering into large, invisible structures. These structures, dark matter halos, formed first, and then, slowly, ordinary matter fell into them, like mist settling into valleys, and where enough matter gathered, stars began to form, then galaxies, then clusters. So in a quiet way, dark matter shaped the universe before anything visible existed. It created the framework, the scaffolding, the hidden architecture upon which everything else was built, and yet, even now, we do not know what it is. We have ideas, possibilities. Perhaps it is made of new kinds of particles, ones that pass through ordinary matter almost without interaction. Perhaps it behaves in ways we do not yet fully understand. But despite decades of searching, we have not directly detected it. We know it is there, because of what it does, not because of what it is. And there is something quietly humbling in that, to realize that most of the structure in the universe, most of what holds it together, is something we cannot see, something that flows through us even now unnoticed. A silent presence, shaping the cosmos from behind the scenes, and as we continue, we'll begin to see how this invisible structure connects to something even larger. Because while dark matter gathers things together, there is another force, subtle, persistent, that is slowly pulling everything apart. If dark matter forms a kind of invisible skeleton, then what exactly does that skeleton look like? It's a quiet question, but one that leads to a surprisingly beautiful answer. Because when astronomers began mapping the positions of galaxies, not just where they appear in the sky, but how far away they are, they expected something fairly simple. They imagined galaxies might be scattered more or less evenly, like grains of sand sprinkled across a surface, not perfectly uniform perhaps, but roughly spread out in all directions. Instead, what they found was something very different. Galaxies were not evenly distributed at all. They gathered, they stretched, they arranged themselves into patterns, long, delicate filaments, like strands of silk, connecting dense clusters of galaxies, sheets and walls of matter spanning hundreds of millions of light years. And between these structures, vast regions where almost nothing existed. These regions are called cosmic voids, and together the filaments, clusters, and voids form what is known as the cosmic web. If you could step back far enough to see the universe on its larger scales, it would not look like a uniform mist of stars. It would look more like a kind of foam, or a sponge, or perhaps something like bubbles in a slowly settling liquid. Thin, glowing threads, surrounding enormous empty spaces. It's a pattern that feels almost organic, not chaotic, but not rigid either. A quiet balance between structure and absence. And what's most striking is this. Most of the universe, by volume, is not in the filaments, not in the galaxies, but in the voids. The empty regions dominate. They are not small gaps between structures. They are the main feature. The structure we see, the galaxies, the clusters, is the exception. To understand just how empty these voids can be, it helps to consider a specific example. There is a region known as the Butter's Void. It is roughly 300 million light-years across. To put that into perspective, light, which moves faster than anything else in the universe, would take 300 million years to travel from one side of this void to the other. And within that enormous space, there are only a handful of galaxies, perhaps a few dozen, in a region where you might expect thousands. If you were inside such a void, looking out into the night sky, your view would be profoundly different from ours. There would be no bright band of the Milky Way stretching across the sky, no nearby galaxies glowing faintly in the distance, just darkness, perhaps a few distant points of light, barely visible, and beyond them, nothing. It would be a universe that feels almost entirely empty, and yet that emptiness is not random. It is shaped, defined, connected to everything else, because the cosmic web is not static. It evolves. Matter flows through it. Slowly, over immense spans of time, material moves away from the emptiest regions and toward the denser ones, from voids into filaments, from filaments into clusters. It's a gentle process, not like rivers rushing or winds blowing, but more like a slow settling, like fine particles drifting in still water, gradually gathering into patterns. And this movement creates a kind of contrast. The denser regions become richer, the emptier regions become emptier, a quiet separation, growing more pronounced over time. You might imagine it like a loaf of bread rising. Air pockets expand within the dough, pushing material aside. The bubbles grow larger, and the walls between them become thinner and more defined. In a similar way, cosmic voids expand as matter leaves them, and the structures surrounding them, filaments and clusters, become more distinct. This gives the universe its large-scale shape, not a uniform spread, but a network, a web of matter stretched across unimaginable distances. And here is something subtle, but important. Voids are not simply places where nothing ever happened. They are places where less happened. Regions that began with slightly less matter than average. Tiny differences, so small they were almost imperceptible in the early universe, have grown over billions of years into these vast empty spaces. It is a reminder that even the largest features of the cosmos can arise from the smallest imbalances. A difference so slight it could be described as 1 part in 100,000, eventually becoming the difference between a galaxy cluster and a cosmic desert. And there is something else, quietly profound about these voids. They change how the universe feels depending on where you are. We happen to live in a relatively dense region. Our galaxy is part of a small group of galaxies, surrounded by others not too far away. The night sky, for us, is rich, layered, filled with points of light. But if we had formed in a deep void, our understanding of the universe might be very different. We might look out and see almost nothing. No evidence of a vast cosmic web. No nearby galaxies to study. No easy clues about the large-scale structure of reality. Our theories, our models, even our sense of what is normal would shift. In a sense, our position in the universe shapes our understanding of it, and we are fortunate. We exist in a place where the structure is visible enough to study, where the web can be traced, where the contrast between matter and emptiness can be observed. But even here, in one of the more populated regions, emptiness still dominates. The distances between galaxies remain vast. The spaces between stars remain immense, and beyond the filaments we can map, there are still larger voids stretching far beyond what we can easily imagine. So the cosmic web is not just a pattern, it is a kind of balance between gathering and dispersing, between structure and space, between something and almost nothing. And as we continue, we'll begin to see that this balance did not arise by chance. It was shaped by the earliest moments of the universe, by events so rapid and so powerful that they stretched tiny fluctuations into the seeds of everything we see today. And in those first moments, the story of emptiness truly begins. If you picture the cosmic web for a moment, those long faint threads of galaxies stretching across the darkness surrounding vast quiet voids, it can be tempting to imagine it as something fixed, a kind of frozen pattern, beautiful but still. And yet, the universe is never truly still, even on its largest scales, even across distances that take like millions of years to cross. There is motion, slow, almost imperceptible, but constant. Matter is drifting, not randomly, but with a kind of quiet direction. And much of that motion is shaped by something that seems, at first, almost paradoxical: emptiness itself. Because voids, the largest, emptiest regions of the universe, do not simply sit there as passive gaps. They influence the movement of everything around them, but not in the way you might expect. A void does not push. There's no force emerging from emptiness that actively drives matter away. Instead, what happens is something more subtle. To understand it, imagine standing in a wide, open valley surrounded by gentle hills. If you release a small ball on the ground, it will naturally roll downhill, moving toward the lowest point, not because something is pushing it from behind, but because gravity is pulling it toward regions of greater mass. Now imagine removing mass instead of adding it. If one region contains less matter than its surroundings, if it is underdense, then there is less gravitational pull coming from that direction. And so, from the perspective of nearby matter, it feels as though there's a kind of outward motion. Not because the void is pushing, but because everything else is pulling more strongly. This creates what scientists sometimes describe in a gentle way as a kind of repeller, a region that matter seems to move away from. But the reality is quieter than that. Matter is simply following the pull of denser regions, flowing toward filaments, toward clusters, toward the places where gravity gathers it. And as it leaves the void behind, the void becomes even emptier. This is a process that unfolds over immense spans of time, hundreds of millions, even billions of years. There are no sudden movements, no dramatic shifts, just a slow migration, a steady drifting, guided by the invisible contours of gravity. You might imagine it like a drop of ink spreading in still water. At first it forms soft patterns, then gradually it thins out in some areas and gathers in others. Over time the contrast becomes clearer. Dense regions become more defined, empty regions become more pronounced, or like a quiet crowd in a large room. People slowly gather into groups, drawn by conversation, by shared focus, while other areas of the room become more open, more spacious. No one is forcing the separation, it simply emerges, and in the universe this separation becomes the cosmic web. Filaments grow denser, clusters become richer, and voids grow larger. This last part is especially important, because voids do not remain the same size. They expand, faster in fact than the average expansion of the universe. This happens because there is less matter inside them, less gravity to slow things down. So as space itself stretches, and we'll soon explore how that stretching works, voids stretch even more. They become more dominant, more expansive, taking up an ever larger fraction of the universe's volume. It is as if the emptiest regions are quietly taking over, not through force, but through absence. And this leads to a deeper realization. The universe is not just empty, it is becoming more empty over time. Structure is not spreading outward to fill the void. Instead, the void is growing around the structure and slowly, gently separating it. You can imagine this like islands in a rising ocean. At first, the islands are close together. You can travel between them easily. But as the water level rises, the distances grow, the connections thin. Eventually, each island stands alone, surrounded by vast stretches of water. In the same way, galaxies and clusters, those bright islands of matter, are becoming more isolated, not because they are moving away from each other through space in the usual sense, but because the space between them is expanding. And within that expanding space, voids stretch and deepen, their emptiness becoming more complete. This process is not something we can observe directly in our daily lives. It unfolds too slowly, on timescales far beyond a human lifetime, but we can measure it by observing how galaxies move, by tracking how light shifts as it travels across space, by mapping the large-scale structure of the universe, and what those measurements reveal is consistent. Matter flows out of emptier regions toward denser ones, voids expand, structure sharpens, and over time, the contrast between something and nothing becomes more extreme. There is something almost poetic in that. The idea that emptiness is not just a backdrop, but an active participant, not by pushing or forcing, but by quietly shaping the paths that matter can take, guiding it indirectly into the forms we see, and then, just as quietly, allowing those forms to drift apart. Because there is another layer to this story, a deeper influence that affects not just how matter moves within the cosmic web, but how the entire web itself evolves, a force, or perhaps a property of space, that is causing the universe not just to expand, but to expand faster over time. And as we move forward, we'll begin to explore that idea, because it is this gentle acceleration, this subtle stretching of space, that ultimately explains why emptiness is not just present in the universe, but growing. If you gently trace the story backward, from galaxies to clusters to the vast web of structure stretched across space, you eventually arrive at a time when none of it existed. No galaxies, no stars, no filaments threading the darkness, just a universe that was, in a quiet and surprising way, almost the same everywhere. It's a difficult idea to hold at first, because everything we've explored so far has been about contrast, dense regions and empty voids, islands of light surrounded by darkness, structure rising out of emptiness. But in the beginning, that contrast did not exist. The universe was nearly uniform, not perfectly identical in every direction, but close enough that, on large scales, it looked like a smooth, even field, like a calm lake at dawn, flat, still, almost without disturbance. And yet, if you look closely at a calm lake, you might notice something subtle, tiny ripples, so small that you might miss them at first, but present and meaningful. The early universe was like that, almost perfectly smooth, with the faintest traces of variation. We know this because of something called the cosmic microwave background. It is a form of light that fills the entire universe, arriving from every direction. Not bright, not visible to our eyes, but measurable with sensitive instruments. This light is ancient. It has been travelling through space for nearly the entire history of the universe. And when scientists map its temperature, how slightly warmer or cooler it is in different directions, they find something remarkable. The differences are incredibly small, so small that they are often described as being about 1 part in 100,000. To put that into softer terms, imagine a perfectly smooth surface, where almost every point is exactly the same height, and then, here and there are tiny rises and dips, so slight that if you ran your hand across them, you might not even feel the change. That is what the early universe looked like, a near perfect balance, with just the faintest unevenness. And yet those tiny differences carried everything within them, because where the universe was slightly denser, even by a very small amount, gravity had little more to work with, a slightly stronger pull. And that small advantage, over time began to grow. Matter in those regions started to gather, very slowly at first, almost imperceptibly, but steadily. And as more matter gathered, the pull became stronger, which gathered even more matter, a quiet feedback, a gentle amplification of something that began as almost nothing. At the same time, the regions that were slightly less dense began to lose matter, not dramatically, just a gradual drifting away as material was pulled toward denser areas, and over immense spans of time, this process created contrast. The smooth lake began to ripple more clearly. The tiny variations became visible structure. Galaxies formed in the denser regions, voids expanded in the emptier ones, and the cosmic web, the vast pattern we see today, emerged from those early imperfections. It is a strange and beautiful thought that everything we see, every star, every galaxy, every structure, began as a difference so small it could almost be ignored, a slight imbalance, a whisper of variation in an otherwise uniform field, and yet without that imbalance, nothing would have formed. If the universe had been perfectly smooth, completely uniform in every direction, then gravity would have had no starting point, no region to favour, no place where matter could begin to gather. Everything would have remained evenly spread. As the universe expanded, it would have simply become thinner and thinner, a fading mist of particles, no stars, no galaxies, no structure, just emptiness, growing more complete over time. So those tiny fluctuations were not just incidental, they were essential. They were the seeds from which everything grew. But this leads to a deeper question. Where did those fluctuations come from? Why was the universe not perfectly smooth? Why were there any ripples at all? To answer that, we have to go back even further, to a time so early that the universe was smaller than anything we can easily imagine. And in that moment, something happened that stretched those tiny differences across the entire cosmos, something that took fluctuations smaller than a particle and expanded them into the structures that would one day become galaxies. But before we step into that moment, it's worth pausing here, just for a breath, to appreciate what this means. The universe you see today, vast, complex, filled with structure, began in a state that was almost completely featureless, and everything that followed emerged from the smallest possible deviations. It is a reminder that even in a system that appears uniform, even in something that feels completely still, there may be hidden patterns waiting to grow, and sometimes it is the smallest differences that shape the largest outcomes. If those first ripples were so small, almost invisible, then something must have happened to make them matter, because a tiny variation on its own is not enough. It needs time, and it needs scale. It needs to be stretched, carried outward, given room to grow. And that is where one of the most remarkable ideas in modern cosmology enters the story. An idea that describes a moment when the universe expanded not just steadily, but almost explosively. A moment when space itself grew so quickly that distances changed faster than anything we can easily imagine. This idea is known as inflation. But rather than thinking of it as a technical concept, it helps to imagine it as a kind of sudden unfolding. Picture a small balloon. At first it is soft, compact, almost featureless. Now imagine that balloon being stretched, not gradually, but almost instantly, expanding so fast that any tiny markings on its surface are pulled apart, smoothed, and spread across a much larger area. What was once close together becomes distant. What was once barely noticeable becomes visible. In a similar way, the early universe is thought to have undergone a period of extremely rapid expansion. In a fraction of a second, so brief that even calling it a moment feels too long, space expanded by an enormous factor. distances grew not by a little, but by something like doubling again and again, over and over, in a rapid sequence. If you imagine doubling something, once it becomes twice as large. Doubling it again makes it 4 times as large, and if you continue this process many times in quick succession, the growth becomes extraordinary. What begins as something tiny quickly becomes vast. This is the kind of growth inflation describes, a rapid stretching of space itself. And this stretching had a profound effect, because those tiny fluctuations we spoke about, the faint ripples in the early universe, were also stretched. At first, they existed on scales far smaller than anything we could observe, perhaps even smaller than individual particles. But as space expanded, those fluctuations were carried outward, pulled across larger and larger regions, until they became the seeds of structure on cosmic scales. It's as if the universe took its smallest irregularities and magnified them, turned them into the blueprint for everything that would follow. Without inflation, those fluctuations might have remained too small, too subtle to grow into galaxies. The universe might have stayed too uniform, too smooth. But with inflation, the tiny became significant. The almost invisible became the foundation of structure. And there is something else inflation helps explain. Earlier, we described the universe as being almost the same in every direction, nearly uniform. That too is surprising, because in a universe that expands normally, different regions would not have had enough time to communicate with each other. Light, moving at its incredible speed, can only travel so far in a given time, so regions far apart should not have been able to exchange information to balance out their properties. And yet, when we look at the cosmic microwave background, we see that distant regions have nearly identical temperatures, almost as if they were once in close contact. Inflation offers a gentle resolution to this puzzle. Before the rapid expansion, the universe was much smaller, compact enough that different regions could interact, exchange energy, and come into balance. Then, during inflation, that small, uniform region was stretched outward, becoming the vast universe we see today. So what appears now as distant and disconnected was once close together. A single, unified patch, expanded across unimaginable distances. It's a bit like taking a small, evenly coloured piece of fabric and stretching it across a large frame. The colour remains consistent even though the size has grown enormously. Inflation preserves that uniformity, while still allowing tiny variations to exist. And those variations, stretched across space, become the seeds of everything. But there is something quietly poetic in this idea. The thought that the largest structures in the universe, galaxies, clusters, the cosmic web itself, may have originated from fluctuations so small they were almost nothing, from tiny uncertainties, subtle variations in the fabric of reality, and through a brief, powerful expansion, those variations were given space to grow. It suggests that the universe is not just shaped by grand forces and vast energies, but also by the smallest possible differences. Differences that, given enough time and enough room, can evolve into something immense. And yet, even with inflation, even with these stretched fluctuations, the outcome was not guaranteed. There was still a delicate balance at play, a balance between expansion and gravity, between spreading out and pulling together. Too much expansion, and matter would drift too far apart to ever form structure. Too much gravitational pull, and everything might collapse too quickly, forming dense objects without the rich variety we see today. Somehow, the universe found itself in a narrow range where both processes could occur, where matter could gather, but not too quickly, where space could expand, but not so much that structure became impossible. And in that balance, galaxies formed, stars ignited, planets emerged, and Eventually observers, like us, appeared, able to reflect on it all. So inflation does more than explain how the universe expanded. It connects the smaller scales to the largest. It shows how something almost imperceptible can shape everything that follows, and as we continue, we'll begin to explore just how delicate that balance truly is. Because the universe, as it turns out, exists in a kind of narrow window, a range of conditions where structure is possible, and outside of that window, there would be almost nothing at all. If you follow this story gently, from a nearly uniform beginning, through the stretching of space into the first seeds of structure, you begin to sense something quiet but remarkable. The universe did not just become complex, it became complex under very specific conditions. Conditions that could have been slightly different and produced a very different outcome. Because once those early fluctuations were stretched across space, and once matter began to gather under gravity, the next question becomes almost inevitable. How much gathering is too much, and how little is too little? Because gravity, left unchecked, does not stop at forming stars or galaxies. It continues, pulling matter inward, increasing density, deepening collapse. If everything were just a little denser in the beginning, those tiny fluctuations might have grown too quickly. Instead of forming gentle structures, galaxies with swirling arms, clusters bound together across vast distances, matter might have collapsed into dense, compact objects almost immediately. Black holes could have formed everywhere, regions of space where gravity becomes so strong that nothing, not even light, can escape. In such a universe, there would still be structure, but it would be extreme, harsh, dominated by collapse rather than balance. On the other hand, if the universe had been just a little less dense, if those early fluctuations were slightly smaller, or if matter were spread just a bit more evenly, then gravity might not have been strong enough to bring anything together at all. Matter would drift. Expanding space would carry everything farther apart, and before stars could ignite, before galaxies could form, the universe would become too thin, too diffuse. A quiet, expanding emptiness, with no islands of light, no structure, no places for complexity to arise. So between these two extremes, too much collapse and too much expansion, there exists a narrow window, a range of conditions where structure can form, but not overwhelm itself, where matter gathers, but does not fall entirely inward, where stars can ignite, shine, and evolve, where galaxies can form stable shapes, persist for billions of years, and interact in gentle ways. And this balance depends on several factors, all working together. The amount of matter in the universe, the strength of gravity, the rate at which space expands, and the nature of the fluctuations themselves. Even small changes in any of these could shift the outcome. Imagine for a moment adjusting the density of matter in the early universe by just a tiny fraction, not doubling it, not halving it, just a slight increase or decrease. That small adjustment would ripple forward through time, changing how quickly structures form, altering the balance between collapse and expansion, leading eventually to a universe that looks very different from the one we see. This is sometimes described as a kind of fine balance, not necessarily something designed, but something that exists within a narrow set of possibilities, and within that narrow set, structure becomes possible. Dark matter plays an important role in this balance, because as we explored earlier, it does not interact with light. It does not feel the pressure of radiation in the early universe, so it can begin to gather sooner, forming the first gravitational wells. These wells act like quiet basins, places where ordinary matter can later fall. Without dark matter, ordinary matter would have struggled to form structure on its own. The early universe was filled with radiation, light pushing outward, resisting collapse. Dark matter, unaffected by that push, provided a kind of early framework, a way for structure to begin forming even while ordinary matter was still being held back. So in a sense, dark matter helped tip the balance. Not too far, but just enough. Allowing structure to emerge without overwhelming the universe. And yet, even with dark matter, the outcome was not guaranteed. Because there is another influence, one we've only briefly touched on so far, the expansion of space itself. From the beginning, the universe has been expanding, stretching outward, increasing the distance between objects, and this expansion works against gravity. It pulls things apart, even as gravity tries to pull them together. So once again, we see a balance. Gravity gathers, expansion separates, and structure exists in the space between those two tendencies. Too much gravity and everything collapses. Too much expansion and nothing forms. But in the universe we observe, those forces exist in a kind of quiet tension. Neither one completely dominating the other, at least not in the early stages, and this allowed for a period of cosmic history where structure could grow, where galaxies could form, where stars could ignite and shine for billions of years, where planets could emerge, and where eventually life could take hold. It is a delicate picture, one where the universe is not simply empty, nor completely full, but balanced in a way that allows complexity to exist. And yet there is something important to notice here. This balance does not last forever. Over time, the influence of expansion begins to change. What was once a gentle stretching becomes something more significant. And as that happens, the balance begins to shift. The same conditions that once allowed structure to form will eventually lead to a universe where structure can no longer sustain itself. So the very balance that made everything possible also contains the seeds of its gradual undoing. But before we move into that unfolding story, there is one more idea to explore. Because when we look at this balance, this narrow window where structure is possible, it raises a quiet question. Why this range? Why these conditions? Why a universe where emptiness is so dominant, yet structure is still able to emerge? And one way of approaching that question is through a simple, almost reflective idea, that we observe the universe the way it is, because only in such a universe could observers exist at all. If you sit with that last thought for a moment, it begins to feel quietly profound, that the universe appears the way it does, not simply by chance, but because only certain kinds of universes allow something like us to notice them at all. It's a gentle shift in perspective. Instead of asking, why is the universe like this? We begin to ask, what kind of universe would allow observers to exist? And in that question, something interesting happens. Because many of the conditions we've been exploring, the balance between gravity and expansion, the size of early fluctuations, the amount of matter in the universe, begin to take on a different kind of meaning. Not as isolated facts, but as part of a larger picture. A picture where the universe is, in a sense, just right. Not perfect, not finely tuned in every detail, but within a range where complexity is possible, where structure can emerge, where stars can shine long enough for something to observe them. This idea is often called the anthropic principle. But instead of thinking of it as a technical term, it helps to see it as a simple observation. We exist in a universe that allows existence, and that statement, though it sounds almost obvious, carries a deeper implication. Because if the universe were even slightly different, we might not be here to notice it. Imagine for a moment a universe where matter was far more concentrated, where the density of the early universe was higher, even by a small amount. In such a universe, gravity would have been stronger in its effects. Matter would collapse more quickly, structures would form rapidly, but they might not be stable. Galaxies could become dense, chaotic environments. Stars might form in bursts, burning quickly, living short lives. Black holes could become more common, dominating regions of space. In that kind of universe, there would still be structure, but it might be too intense, too unstable for long-lived systems to emerge. Planets might not have time to form, or if they did, they might exist in environments too extreme for complexity to develop. Now imagine the opposite, a universe where matter is just a little less dense, where those early fluctuations were slightly weaker. In this case, gravity would struggle to bring matter together. Structures would form slowly, or perhaps not at all. Gas would drift apart as space expands. Stars might never ignite. Galaxies might never take shape. The universe would become a quiet, expanding field of particles, growing thinner with time. No stars, no light, no complexity. So between these two possibilities, too much structure and not enough, there exists a narrow middle ground, a range where the universe is not too crowded and not too empty, where structure can form but does not overwhelm itself, where stars live long enough to create heavier elements, where planets can form, where chemistry can become complex, and where eventually awareness can arise. In this sense, the emptiness of the universe is not a flaw. It is a condition, a necessary feature of a universe that supports structure. Because if space were filled more densely with matter, if galaxies were packed closely together, if stars were everywhere, the dynamics would change. Interactions would become more frequent. Gravitational disturbances would increase. Stable systems, like the one we live in, might be far less common. Emptiness provides separation. It creates distance. It allows structures to exist without constantly interfering with one another. It gives galaxies room to form, stars room to evolve, planets room to orbit. In a way, emptiness is what makes stability possible. It is the quiet space between things that allows those things to exist. You might think of it like a conversation. If every voice was speaking at once with no pause, no silence between words, meaning would be lost. But with space, small gaps, moments of quiet, understanding becomes possible. In the same way, the universe needs space, not just physically, but structurally. And there is another layer to this, because the balance we've been describing does not depend on just one factor. It depends on several. The strength of gravity, the rate of expansion, the amount of matter, the nature of dark matter, the size of the initial fluctuations. Each of these plays a role, and each must fall within a certain range for structure to emerge. If one changes too much, the outcome shifts. And this leads to a kind of quiet realization that the universe, as we observe it, exists within a narrow set of possibilities, not infinite in its outcomes, but constrained, balanced. And within that balance, emptiness is not just present, it is dominant. Most of the universe is empty, because that is what allows the rest to exist. But this also leads to something more subtle, because even though emptiness is necessary, it is not the whole story. There is still something missing, something we have not fully accounted for. Because when we measure the universe, when we carefully observe how galaxies move, how structure forms, how space expands, we find that most of what exists is not just empty, it is unknown. We can see stars, we can measure galaxies, we can trace the cosmic web. But all of that, the visible universe, makes up only a small fraction of the whole. The rest is something else, something we cannot see directly, something that shapes the universe in ways we are still trying to understand. And this brings us to the next part of the story. Because to understand why the universe is becoming more empty, we have to understand what the universe is made of, and, perhaps more importantly, what it is not. If the universe exists within such a delicate balance, then there is another quiet realization waiting just beneath the surface. Structure is not guaranteed, not even something as familiar as a galaxy. Because when scientists began to look closely at how galaxies form and evolve, they found something slightly unsettling. The process is almost too efficient, too stable, too well structured, as if something is helping things along in a way we don't fully understand. Let's begin with a simple picture. Imagine a cloud of gas drifting through space, cold, diffuse, spread out over a vast region. This is how many galaxies begin. Over time, gravity pulls that gas inward. It gathers, becomes denser, and eventually stars begin to form. This part makes sense. Gravity brings things together, density increases, stars ignite. But when we try to simulate this process, to recreate it in models and calculations, we often find that it doesn't behave quite the way we expect. Sometimes galaxies form too slowly, sometimes they form too quickly, sometimes they don't settle into stable shapes. And yet, when we look at real galaxies, they are everywhere, not just existing, but organized. Spiral galaxies like the Milky Way have elegant arms that curve outward in smooth patterns. Elliptical galaxies form rounded, glowing structures. Clusters of galaxies arrange themselves into larger systems. It all feels coherent. But why? One of the puzzles involves the rotation of galaxies. If you imagine stars orbiting the center of a galaxy, you might expect their motion to behave like planets around the sun. Closer stars move faster, distant stars move more slowly. But as we explored earlier, that's not what we observe. Stars far from the center move just as quickly as those closer in. This suggests that galaxies are surrounded by much more mass than we can see. Dark matter helps explain this. It provides the extra gravitational pull needed to hold galaxies together. Without it, many galaxies might simply drift apart. But even with dark matter, there are still questions. For example, spiral galaxies. Their arms are not fixed structures. They are more like patterns that move through the galaxy. A bit like waves traveling through water. Stars move in and out of these arms over time. Yet the overall spiral shape remains. Maintaining that structure over billions of years is not trivial. It requires a balance between motion, gravity, and the distribution of matter. Too much disruption, and the arms would break apart. Too little, and they would not form clearly at all. And then there is the question of timing. In the early universe, galaxies appear to have formed quite rapidly, faster than some models predicted. Observations from powerful telescopes have revealed galaxies that are already large and structured at times when the universe was still very young. This suggests that the process of formation may be more efficient or more complex than we fully understand. It's as if the universe found a way to organize itself more quickly than expected. And that raises a quiet possibility that the formation of galaxies is not just a simple outcome of basic laws, but the result of several factors aligning just right. Dark matter providing structure, gravity pulling matter inward, cooling processes allowing gas to condense, feedback from stars regulating growth, all working together, not perfectly, but effectively. And this brings us back to the idea of fragility. Galaxies feel permanent when we look at them, stable, enduring. But in reality, they exist within a narrow set of conditions. Change those conditions slightly, and the outcome shifts. If dark matter behaved differently, galaxies might not hold together. If gas could not cool efficiently, stars might not form. If gravitational interactions were stronger or weaker, structures might become chaotic or dissolve entirely. So the galaxies we see are not inevitable, they're possible, and that distinction matters, because it reminds us that structure in the universe is not the default state. It is something that emerges under the right conditions and persists only as long as those conditions remain favourable. There is also something quietly humbling in this, because when we look at the night sky or at images of distant galaxies, it's easy to feel as though structure is everywhere, as though the universe is rich and full of form. But what we are seeing are the successful cases, the places where everything came together just right. We are not seeing the vast regions where nothing formed, the empty stretches where matter remained too diffuse, the voids where structure never emerged. In that sense, galaxies are like rare patterns, appearing in a much larger background of emptiness. And even within those patterns, there is a constant tension. Galaxies merge, collide, change shape over time. Stars are born and eventually fade. Nothing is truly static. Everything is in motion. Everything is evolving. So when we say that galaxies exist, what we really mean is that, for a time, under certain conditions, matter has arranged itself into these forms. Forms that feel stable to us, because they last for billions of years. But in the larger story of the universe, even billions of years is just a phase, a chapter. And as we move forward, we begin to see that this chapter is not permanent, because there is something else shaping the universe, something that does not gather matter, but separates it, something that acts not within galaxies, but across the vast distances between them. And it is this influence that will slowly change the balance we've been exploring, turning a universe where structure is possible into one where structure begins to fade. If galaxies are not guaranteed, if structure itself depends on a careful balance, then there is another quieter question that begins to form. What exactly is the universe made of? Because so far we've spoken mostly about what we can see. Stars, galaxies, gas drifting between them, the luminous parts of the cosmos. But when scientists began to measure the universe more carefully, not just observing where things are, but how they move, how they bend light, how they evolve over time, they discovered something unexpected, something that, in a gentle way, changes the entire picture. Most of the universe is not made of anything we can directly observe. If we take everything we can see, every star, every planet, every cloud of gas, and add it all together, it accounts for only a small portion of the total, roughly 5%. That means that about 95% of the universe is something else, something dark. Not necessarily in the sense of being empty, but in the sense of being invisible, hidden from direct view. We've already met one part of this hidden majority, dark matter, the unseen mass that holds galaxies together, that shapes the cosmic web, that provides the gravitational framework for structure to form. But dark matter is only part of the story. There is another component, something even more mysterious, something that does not just influence how matter moves, but how space itself behaves. We'll come to that soon. For now, it's worth pausing with this realization that most of the universe is not only empty, but also unknown. We are surrounded in every direction by something we cannot see, something that passes through us, through planets, through stars, without leaving a direct trace. It's a bit like living in a house where most of the structure is invisible. You can see the furniture, the surfaces, the things that reflect light, but the walls themselves, the beams that hold everything together, are hidden. You can infer their presence, you can feel their effects, but you cannot observe them directly, and yet without them, the house would not stand. In a similar way, the visible universe is only the surface. The deeper structure remains unseen, and this creates a kind of quiet tension in our understanding, because on one hand, we have a model of the universe that works remarkably well. It explains how galaxies form, how structure evolves, how light travels across space. But on the other hand, most of what that model depends on is not directly observed. We know dark matter is there because of its gravitational effects, because of how galaxies rotate, because of how clusters hold together, because of how light bends when it passes near massive objects, a phenomenon known as gravitational lensing, where space itself is curved, gently redirecting the path of light. These are indirect clues, careful measurements, consistent patterns, but they point to something we cannot yet fully describe. And then there is the other component, the one that affects not just matter, but the expansion of the universe itself, a presence that seems to act everywhere, even in the emptiest regions of space. For now, we can think of it simply as part of the missing universe, because when we measure how fast the universe is expanding and how that expansion changes over time, we find that something is influencing it in a way that cannot be explained by matter alone, something that appears to push space outward, not in a forceful, dramatic way, but gently, persistently, as if emptiness itself carries a kind of energy. We will explore that idea more deeply soon, but even before we do, there is something quietly important to notice. The fact that most of the universe is unknown does not make it chaotic, it does not make it unpredictable. In many ways, the universe behaves with remarkable consistency. The same physical laws apply across vast distances. Patterns repeat, structures form in recognizable ways. So even though we do not yet know what most of the universe is made of, we can still trace its effects. We can still understand its influence. It's a bit like hearing music from behind a wall. You cannot see the instruments. You cannot watch the performers, but you can hear the melody. You can feel the rhythm. You can begin to understand the structure of the piece, even without seeing its source. And in the same way, we're beginning to understand the hidden parts of the universe, not by observing them directly, but by listening to how they shape everything else. There's also something humbling in this, to realize that everything we experience, the stars we see, the galaxies we study, the matter that makes up our own bodies, is only a small fraction of what exists. We are, in a sense, living within the visible edge of something much larger, something mostly unseen, and perhaps mostly empty, but not entirely, because even within that emptiness, there is structure, there is influence, there are forces at work that shape the evolution of the cosmos, and as we move forward, we will begin to explore one of the most important of those forces, a force that does not gather matter, but spreads it apart, a force that acts not only within galaxies, but across the entire universe, and it is this force, more than anything else, that explains why the universe is becoming more empty over time. Up to this point, the story has been one of balance, gravity gathering matter, small differences growing into structure. A universe that, while mostly empty, still finds ways to form galaxies, stars, and everything we see. And if we had paused here, if we had asked scientists a few decades ago what would happen next, they might have given a simple answer. The universe is expanding, yes, but over time, gravity should slow that expansion down, like a ball thrown upward. It rises quickly at first, then gradually slows, perhaps even turning around and falling back. This was the expectation. A universe that begins with a rapid expansion, and then gently decelerates under its own gravity. And for a long time, that seemed reasonable. But in the late 20th century, astronomers began to test this idea more carefully. They wanted to measure how the expansion of the universe was changing over time, not just whether it was expanding, but whether that expansion was slowing down. To do this, they needed a way to measure very large distances so vast that ordinary methods would not work, and so they turned to something known as a Type 1 supernova. Now that may sound technical, but the idea can be understood in a very simple way. A Type 1a supernova is a kind of stellar explosion. A star reaches a critical point, and then, in a brief and powerful event, it releases an enormous amount of light. For a short time, it can shine as brightly as an entire galaxy. But what makes these explosions especially useful is that they tend to reach a similar brightness each time. Not exactly identical, but close enough that they can serve as what astronomers call standard candles, objects whose true brightness is known. And if you know how bright something truly is, you can compare it to how bright it appears from Earth. If it appears dimmer than expected, it must be farther away. If it appears brighter, it must be closer. It's a bit like looking at a row of identical lamps stretching into the distance. The farther lamps appear dimmer, not because they are weaker, but because they are farther away. So by observing these supernovae in distant galaxies, astronomers could estimate how far away those galaxies were. And by measuring how the light from those galaxies was stretched, shifted toward longer wavelengths as it travelled through expanding space, they could also estimate how fast those galaxies were moving away from us. Combining these two pieces of information, distance and speed, they could begin to map how the expansion of the universe had changed over time. It was a careful, patient process, observing distant explosions, measuring faint signals, comparing results across many galaxies. And then, slowly, a pattern began to emerge, but it was not the pattern they expected. Instead of finding that the expansion was slowing down, they found that it was speeding up. Galaxies were not just moving away from us, they were accelerating away. The farther away a galaxy was, the faster it appeared to be receding, in a way that suggested the expansion of space itself was increasing over time. It was a surprising result, quietly unsettling, because it meant that gravity was not the only influence shaping the large-scale behaviour of the universe. Something else was at work, something that was counteracting gravity. Not by pulling matter together, but by pushing space apart. At first, this idea was met with caution. Perhaps there was an error in the measurements. Perhaps the supernovae were not as uniform as expected. Perhaps some detail had been overlooked. But as more observations were made, as different teams studied the same phenomenon, the result held. The expansion of the universe is accelerating. And this discovery changed the story, because it meant that the balance we've been describing, the quiet tension between gravity and expansion, was not stable over time. It was shifting. Gravity still gathers matter on smaller scales. It still forms galaxies, stars, and clusters, but on the largest scales, something else is becoming dominant. Something that grows stronger as space expands. Something that becomes more influential as the universe becomes more empty. It is a subtle idea, because this influence does not act like a force in the usual sense. It does not pull objects through space. Instead, it affects space itself. It changes how distances grow over time. You might imagine it like a gentle stretching. At first, barely noticeable, but gradually increasing, so that over time the space between distant objects grows faster and faster. And because this effect is spread throughout all of space, it becomes more significant as the universe expands. More space means more of this effect, which leads to more expansion, which creates even more space, a quiet feedback loop, a steady acceleration, and this has profound consequences, because it means that the universe is not just expanding, it is expanding in a way that will eventually separate structures from each other. Galaxies that are not bound together by gravity will drift farther and farther apart. Clusters will become isolated. The cosmic web will stretch, and the vast emptiness between structures will grow even larger. It is as if the universe is slowly loosening its own connections, allowing everything to drift apart, not suddenly, not violently, but gently, persistently, over immense spans of time. And at the heart of this process is something we have not yet fully understood, something that appears to be woven into the fabric of space itself, something that becomes more important as the universe becomes more empty. As we move forward, we'll begin to explore this idea more directly, because whatever this influence is, it is one of the most important clues to why the universe is becoming what it is, a place where emptiness does not just exist, but grows. If the universe is not just expanding, but accelerating in its expansion, then something must be shaping. That change, something subtle, something that becomes more important as space itself grows. And for a long time, scientists struggle to describe what that something might be, because it does not behave like ordinary matter, it does not gather into structures, it does not form stars or galaxies, it does not clump or cluster. Instead, it seems to be spread out evenly, everywhere, even in the emptiest regions of space, and perhaps most intriguingly, it appears to grow in influence as the universe expands. This mysterious component is what we now call dark energy. But like dark matter, the name is less an explanation, and more a way of pointing to something we do not yet fully understand. To get a gentle sense of what dark energy might be, it helps to begin with an unusual idea. That empty space is not truly empty. That even in a region with no stars, no gas, no particles, there may still be something present. A kind of background energy, not visible, not directly, measurable in a simple way, but real enough to influence the behavior of the universe. Imagine for a moment a perfectly quiet room. No sound, no movement. It feels empty. But if you listen closely enough, you might notice subtle vibrations, the faint hum of distant activity, something that is always there, even when nothing obvious is happening. In a similar way, space itself may carry a kind of energy, a baseline presence, and as the universe expands, as more space comes into existence, just there is more of this energy, which leads to a curious effect, because if energy is spread throughout space, and space increases, then the total amount of that energy also increases. More space, more energy, and that energy appears to act in a way that gently pushes space outward, not like a force applied at a point, but like a property of space itself, a tendency to expand. You might imagine it like a very soft pressure, evenly distributed, acting everywhere at once. At first, when the universe was smaller and denser, this effect was relatively weak compared to gravity. Gravity pulling matter together dominated the behavior of the cosmos. Galaxies formed, structures grew, the cosmic web took shape. But as the universe expanded, as matter became more spread out, the influence of gravity weakened on large scales. Meanwhile, the influence of dark energy did not diminish. It remained constant, or at least close to constant, per unit of space. And so, over time, the balance shifted. Dark energy became more significant, more influential, until eventually it began to dominate the expansion of the universe. This is why the expansion is accelerating, not because galaxies are moving faster through space in the usual sense, but because space itself is stretching more rapidly over time, and dark energy appears to be the reason. There is an older idea in physics that connects to this, an idea introduced by Albert Einstein long before the discovery of accelerating expansion. He proposed something called the cosmological constant, a term that could be added to the equations describing gravity, not to pull things together, but to provide a kind of uniform influence throughout space. At the time, this idea was introduced for a different reason. Einstein was trying to describe a universe that did not change, one that was static. Later, when it became clear that the universe was expanding, he set the idea aside. But after the discovery of accelerating expansion, the concept returned, not as a way to keep the universe static, but as a way to describe the energy of empty space. Today, many models of dark energy are based on this idea that empty space has an intrinsic energy, a constant presence. But there is a quiet tension here, because when scientists try to estimate how much energy empty space should contain, based on our understanding of quantum physics, the result is vastly larger than what we observe, not just a little larger, but dramatically so. A difference so extreme that it's often described as one of the greatest mismatches between theory and observation in all of physics. And yet, despite this mismatch, the observed effect is clear. The universe is accelerating. Dark energy, whatever it is shaping the large-scale behavior of the cosmos. And this leads to a deeply intriguing idea, that emptiness is not neutral. It is not simply the absence of matter. It has properties. It has influence. It participates in the evolution of the universe. In fact, it may be the dominant factor in determining the universe's long-term future, because as space continues to expand, dark energy continues to act, and over time, its influence becomes more pronounced. Galaxies that are not gravitationally bound will drift farther apart. Clusters will become isolated. The cosmic web will stretch and thin, and the vast voids we spoke about earlier will grow even larger, more empty, more dominant. It is a quiet transformation, not something that happens suddenly, but something that unfolds over billions, trillions of years. And through it all, dark energy remains, steady, persistent, a presence woven into the fabric of space, and there is something almost poetic in that the emptiest parts of the universe may hold the key to its ultimate fate, that what we once thought of as nothing may in fact be one of the most important somethings in existence. And as we continue, we will begin to explore what this means for the future. Because if the expansion of the universe continues to accelerate, then the distances between structures will grow not just larger, but unreachable, and slowly, gently. The universe we can observe today will begin to slip beyond our view. As the influence of dark energy becomes stronger, the story of the universe begins to change in a quiet but profound way, not suddenly, not in a dramatic collapse or explosion, but in something far more subtle, a gradual separation, a slow drifting apart of everything that is not tightly bound together. To understand this, it helps to return to a familiar image, the expanding balloon. Imagine small dots drawn on the surface of a balloon. As the balloon inflates, the dots move away from each other, not because they're travelling across the surface, but because the surface itself is stretching. Now imagine that some of those dots are connected by strong bonds. They form small clusters. As the balloon expands, those clusters remain intact. The connections within them are strong enough to resist the stretching, but the distance between different clusters continues to grow, slowly at first, and then more noticeably. This is how the universe behaves. Within galaxies, gravity is strong. Stars orbit the centres of their galaxies. Planets orbit stars. These systems are bound together. The expansion of space does not pull them apart. The same is true for groups of galaxies that are gravitationally connected. Our own galaxy, the Milky Way, and its nearest neighbour Andromeda are part of a small group. They are actually moving toward each other. In billions of years, they are expected to merge. On these scales, gravity still dominates. But beyond these local structures, something else takes over. Galaxies that are not bound together begin to drift apart, and as dark energy continues to influence the expansion of space, that separation increases. The farther away a galaxy is, the faster it appears to recede. Not because it is moving through space at extraordinary speeds, but because the space between us and that galaxy is stretching. And as this stretching accelerates, a remarkable effect begins to emerge. There comes a point where distant galaxies move away from us so quickly, due to the expansion of space, that the light they emit can no longer reach us. Not because the light stops travelling, but because the space it must cross is expanding faster than the light can traverse it. It's like trying to walk across a moving walkway that is speeding up beneath your feet. If the walkway moves slowly, you can make progress. If it moves too quickly, you may find yourself unable to reach the other side. In the universe, this creates what is known as a cosmic horizon, a boundary beyond which events can no longer affect us, not because those regions cease to exist, but because their light will never reach us again. And as the universe continues to expand, that horizon effectively closes in, not by moving inward in a physical sense, but by allowing more and more distant regions to slip beyond our reach. Galaxies that we can observe today will, in the distant future, fade from view. Their light will become more stretched, more red, more faint, until eventually it disappears from the observable sky. This process is not something we will notice in our lifetimes. It unfolds over timescales far beyond human experience. But it is happening. Even now, the universe is not just expanding, it is becoming less observable, less connected, less filled with visible structure. You might imagine it like standing on a shoreline watching distant ships. At first, they are clearly visible, their lights steady, their shapes defined. But as they move farther away, they grow dimmer, their outlines blur. Eventually they slip below the horizon, not because they have vanished, but because they have moved beyond what you can see. In the same way, distant galaxies are slowly disappearing from our observable universe, and over vast stretches of time, this effect will become more pronounced. Future observers, if any exist, will see a very different sky. Instead of a universe filled with galaxies in every direction, they may see only their own local group, a handful of galaxies bound together by gravity. Everything else gone from view. The cosmic web, once vast and interconnected, will appear to dissolve. Not because it no longer exists, but because its distant parts are no longer visible. And there is something quietly unsettling in this idea, because it means that we are living in a special moment, a time when the universe is still rich with observable structure, when light from distant galaxies still reaches us, when we can study the large-scale shape of the cosmos. In the distant future, that may no longer be possible. The evidence of the universe's history, its expansion, its structure, its origins, will become harder to detect. Eventually it may disappear entirely from observation, leaving only a small, isolated region, a quiet island of matter in an expanding sea of space. And within that island, observers might look out into the darkness and see nothing beyond their local surroundings. No distant galaxies, no cosmic microwave background, no clear signs of a larger universe. They might conclude that the universe is small, static, limited to what they can see, unaware of the vast structure that once existed beyond their horizon. It is a gentle reminder that what we observe is shaped by when we observe it, that our understanding of the universe depends not only on where we are, but on when we are. And right now, We happen to live in a time when the universe is still revealing itself, still connected, still filled with light from distant places, but slowly, quietly. That connection is fading. The universe is not just expanding, it is, in a very real sense, disappearing. If you imagine the universe far into the future, not millions of years from now, but billions, trillions, a time so distant it almost feels like a dream, the sky begins to change, not suddenly, not in a way that would startle you, but slowly, gently, almost without notice. The stars you see tonight would still be there, at first. Your galaxy would still glow with its quiet spiral of light. Neighbouring galaxies, those faint, distant smudges we can just barely observe with telescopes, would still hang in the darkness. But as time continues, something subtle begins to happen. The distant galaxies begin to drift farther away, not in a dramatic motion, but in a gradual stretching. Their light takes longer to reach you. It becomes softer, fainter, shifted toward deeper shades of red as the space between you and them expands. If you were to watch carefully, over spans of time far beyond a human life, you would notice that the sky is slowly emptying. The most distant galaxies would be the first to fade. Their light stretch so much that it no longer reaches you in a visible form. They do not vanish in an instant. They simply slip beyond what can be seen, like distant candles carried farther and farther away into the night. And over time, more galaxies follow, one by one, quietly disappearing, until eventually only the nearest galaxies remain, those bound together by gravity, those close enough that the expansion of space cannot separate them. In this distant future, the night sky would look very different. There would be no vast field of galaxies stretching into the distance, no sense of a large, interconnected universe. Instead, there would be a small collection of stars and galaxies, your local group, floating in an otherwise empty darkness. It would feel isolated, self-contained, complete in its own way, but disconnected from everything beyond. And there is something even more subtle, something that would not be visible, but would be deeply significant. Right now, if we look carefully, we can detect a faint glow that fills the entire universe, a soft background of radiation, a quiet echo from the earliest moments after the universe began. It is incredibly weak and invisible to our eyes, but with the right instruments, we can measure it, and from it, we learn about the origin of everything we see. In the far future, that glow will still exist, but it will be stretched, diluted, its wavelengths lengthened so much by the expansion of space that it becomes almost impossible to detect, its signal fading into something too weak, too spread out, to be measured. And so, future observers would not see it. They would not know it is there. They would not have access to one of the most important clues about the universe's beginning. And without that clue, something remarkable happens. The story of the universe becomes harder to reconstruct. Imagine trying to understand the history of a place without any records, no maps, no fossils, no traces of what came before, only the present moment and the structures around you. Future observers might look at their local group of galaxies and assume that this is all there is, a small, static system. They might not realize that long ago there were countless other galaxies. That space once connected vast regions, that the universe has been expanding for billions of years. The evidence would be gone, not destroyed, but hidden, carried beyond the horizon of observation. And this leads to a quiet and almost haunting thought that the universe, as we understand it today, is only visible for a limited time. We happen to live in an era when distant galaxies are still within reach, when their light can still travel across space and arrive here, when the faint background glow of the early universe can still be detected. But this era will not last forever. There is a window, a span of cosmic time, during which the universe reveals itself, and we are within that window. Before it, the universe was too dense, too hot, too opaque to observe clearly. After it, the universe will be too empty, too stretched, too disconnected. So this moment, the one we are in right now, is special. Not because it is central, not because it is privileged in any obvious way, but because it is a time when the universe can still be seen as a whole. And in the far future, that wholeness will fade, not violently, not abruptly, but gently, like light dimming at the edge of perception. The sky will grow quieter, darker, less filled with distant structure, until eventually observers, if they exist, will look out into the night and see only a handful of nearby stars and galaxies. And beyond that, nothing. No evidence of a larger cosmos. No sign of the vast web that once stretched across space. Just a small island of light, surrounded by an endless silent darkness. And they might wonder if the universe has always been this way. If you remain in that distant future for a little while longer, beyond the fading of galaxies, beyond the quiet darkening of the sky, the story continues. But it continues in a way that is even slower, even quieter, almost like a gentle fading of warmth from a room that has been left undisturbed for a very long time. Because the disappearance of distant galaxies is not the end of the universe, it is only the beginning of a much longer process. A gradual winding down, a soft approach towards stillness. At first, within those remaining galaxies, the ones still bound together, stars continue to shine. They are born from clouds of gas, just as they always have been. They live for millions or billions of years. And then they fade. Some end quietly, cooling over time. Others end in brief, brilliant moments, releasing their energy into the surrounding space. But over time, something changes. The gas that forms new stars begins to run out. Each generation of stars uses a portion of it, and with each cycle, there is less available for the next. It is not an abrupt shortage, it is a gradual thinning, a slow depletion, like a fire that has plenty of fuel at first, burning brightly, and then, over time, consuming what remains until only faint embers are left. New stars form more slowly, less frequently, until eventually star formation comes to an end. The galaxies that remain are filled with aging stars, long-lived, steady points of light, slowly exhausting their energy. The night sky, even within these galaxies, becomes dimmer, not empty, but quieter, less active, more still. As time continues, even these stars begin to fade. The most massive stars have already lived short, brilliant lives and disappeared. What remains are smaller stars burning more slowly, but even they cannot shine forever. Eventually they exhaust their fuel, they cool, they become faint remnants, dense, dim objects that no longer produce light in the way stars once did. And so, the universe enters a stage where light itself becomes rare. Not gone entirely, but scarce. A memory of what once filled the cosmos. And then there are the black holes, formed from the collapse of massive stars, or from the merging of galaxies. These are some of the most enduring structures in the universe, objects so dense that not even light can escape their pull. For a long time, they remain quiet, invisible except for their influence on nearby matter. They persist long after stars have faded, long after galaxies have grown dim, but even black holes are not eternal. Over extremely long periods of time, timescales so vast that they stretch beyond ordinary comprehension, they begin to lose energy, not through a dramatic process, but through something subtle, a faint emission, a slow release of energy that causes them very gradually to shrink. It is as if they are slowly evaporating, not in the way water evaporates under heat, but in a much quieter, more gradual sense. Over unimaginable stretches of time, even the largest black holes will fade, their mass diminishing, their presence dissolving into the surrounding space. And when that happens, one of the last remaining structures in the universe disappears. What remains then is difficult to picture, because there are no bright stars, no glowing galaxies, no massive structures, only a thin distribution of particles, low energy radiation, and vast stretches of empty space. The universe approaches a state that physicists describe in a very simple way, a state of equilibrium, a condition where energy is spread out as evenly as possible, where there are no significant differences, no gradients, no flows. To understand this, it helps to think of something familiar, a cup of hot coffee. When you first pour it, it is warm. Steam rises, heat flows from the coffee into the surrounding air. But over time, that heat spreads. The coffee cools. The temperature difference between the coffee and the room decreases. Eventually, the coffee reaches the same temperature as its surroundings. At that point, there is no more flow of heat, no more change. Everything is in balance. The universe, in its far future, moves towards something like this, not in terms of temperature alone, but in terms of energy distribution. Energy spreads, differences fade, and without differences, there is no process to drive change, no structure to form, no motion in the sense we are used to, just a quiet, uniform state. And this is sometimes called the heat death of the universe, not because it is hot, but because it has reached a kind of final stillness, a condition where nothing more can happen in any meaningful way. It is not a dramatic ending, not a collapse or an explosion, but a gentle fading, a slow arrival at silence. And there is something almost peaceful in that idea, a universe that begins in intense energy, in rapid change, in dynamic structure, and then, over time, settles, calms, becomes still, like ripples on a lake slowly disappearing until the surface is smooth once more. But this stillness comes at a cost, because along with it comes the loss of structure, the loss of contrast, the loss of everything that once made the universe feel full, and in that sense, the emptiness we've been exploring is not just a feature of space, it is the final state, the direction toward which everything moves. And yet, before we close this story, there is one more layer to consider. Because even in a universe that fades, even in a cosmos that becomes quiet and still, there is something that remains, at least for a time, something that can observe, reflect, and find meaning within all of it. If you've followed this journey all the way here, from a sky that feels full to a universe that is mostly empty, to a future where even light itself begins to fade, then something quiet begins to emerge, a different way of seeing what emptiness means, because at first emptiness can feel unsettling, a universe where most of space contains almost nothing, where galaxies are rare, where structure is fragile, where over time everything drifts apart. It can feel as though emptiness is a kind of absence, a lack, something missing. But as the story unfolds, that feeling begins to soften, because what we have seen is not a universe that failed to be full. It is a universe that required emptiness, a universe where space had to be vast and open for structure to exist at all, where galaxies could only form because there was enough room between them, where stars could shine steadily because they were not constantly disturbed, where planets could orbit quietly, undisturbed by endless collisions. In that sense, emptiness is not the opposite of structure. It is what allows structure to happen, It is the quiet background against which everything else becomes visible. You might think of it like silence in music. If every moment were filled with sound, no pauses, no space between notes, the music would become overwhelming. Meaning would blur. But with silence, with small gaps between tones, patterns emerge. Melody becomes possible. And the same is true of the universe. Without emptiness, there would be no contrast, no distinction between one thing and another, no stable systems, no time for complexity to develop. So emptiness is not simply nothing. It is a condition that allows something to take shape. And there is another layer to this. Because throughout this journey, one idea has appeared again and again. Rarity. Structure is rare. Galaxies are rare compared to the vast volume of space. Stars are rare within galaxies. Planets are rare around stars. And conscious observers, beings capable of reflecting on all of this, are perhaps rarer still. And it is this rarity that gives things their significance. If stars filled every part of the universe, they would no longer stand out. If galaxies were packed together everywhere, their structure would feel ordinary. If awareness were common and constant, it might not feel as remarkable. But because these things are rare, they become meaningful, they become noticeable, they become something to wonder about. And perhaps in a quiet way, this is part of what gives the universe its character. Not abundance, but contrast. Not fullness, but the interplay between emptiness and structure, between silence and sound, between darkness and light. And within that interplay, something else emerges. Awareness, the ability to look at the universe and recognize it, to observe the patterns, to ask questions, to feel curiosity. In a sense, the universe becomes aware of itself through the minds that arise within it. Not everywhere, not continuously, but in small scattered places, tiny pockets of complexity, in an otherwise vast and quiet cosmos. And that idea carries a gentle kind of beauty, that in a universe mostly made of emptiness. There are moments where something looks back, where something notices, where something understands, even partially, what is unfolding. You are one of those moments, a brief point of awareness, in a universe that stretches across unimaginable distances and times. And while that awareness is temporary, while it exists only for a short span, it is still real, it still matters. Not because it changes the universe as a whole, but because it changes how the universe is experienced. It brings meaning into a space that would otherwise be silent, and perhaps that is enough. Not to explain everything, not to resolve every mystery, but to offer a quiet perspective. That the emptiness we see is not something to be feared, but something that allows everything else to exist, that gives shape to structure, that gives context to light, that makes the rare feel meaningful. And so, as we come to the end of this journey, you might return for a moment to that first image, standing beneath a night sky, looking up at the stars, feeling that sense of fullness. And now, perhaps, you see it a little differently, not as a sky crowded with objects, but as a vast, quiet space, where a few points of light shine, rare, scattered, beautiful, because of the emptiness that surrounds them. And so, we've reached the end of tonight's exploration. Whether your eyes are still open or you're already floating somewhere between waking and dreaming, thank you for being part of this little journey. If you'd like to join me again for more gentle wanderings, you're always welcome to subscribe or share this with someone who could use a peaceful pause. Time has a way of slipping through our fingers, but here, in this quiet moment, it's just you and the soft hush of rest. Sleep peacefully, wherever and whenever you may be.